All right, so we're going to start our discussion of matrix multiplication with a special case, and that special case is a row matrix times a column matrix. So we'll start out by refreshing our memories. A row matrix is a matrix that consists of a single row, and likewise, a column matrix is a matrix that consists of a single column. So, in order to multiply a row matrix times a column matrix, they must have the same number of elements. Now, they won't have the same size because their orientation will be different. A row matrix has a single row, so its size will always be 1 by n, where n is some number, however many elements it has. And a column matrix will have the size n by 1. Remember that the rows always come first when we're talking about size or when we're talking about element position in our double subscript notation, which we'll get to in a second. So here we have a rule for multiplying a row times a column when they each have 2 elements. So this is a special case of our special case. So this is really the setup to the rule, not the rule itself. So remember, we have this double subscript notation where the first number represents the row that the element is in. The second number represents the column. So A11 is in row 1, column 1. A sub 12 is in row 1, column 2. And likewise, I've got B sub 11 and B sub 21. B sub 21 is row 2, column 1. This is a row matrix times a column matrix. And the way that we multiply these, we take A sub 11 and we multiply that times B sub 11. So A sub 11, B sub 11. Then we multiply A sub 12 times B sub 21. So first elements together, second elements together. They're not in the same position, but they're the second element in the row times the second element in the column. And what I'm going to do, and this is important, is I'm going to add these two products together. So when you do A sub 11, B sub 11 plus A sub 12 times B sub 21, that gives you a single number. So this is a matrix with a single element. So the result of multiplying a row times a column is still a matrix, but it's a 1 by 1 matrix. There is only one thing in that matrix. It is not a scalar, even though there's only one number. The square brackets are important and do make it a matrix. So let's have some examples of this. So I'll have my formula up at the top there. So I've got my single row times my single column, the nice small 2 element ones, the way that our rule works for. So I've got 10 times 5 plus 3 times 2, and that is my matrix. So when I actually calculate this, 10 times 5 is 50, 3 times 2 is 6, so 50 plus 6 is, of course, 56. So this is a matrix that has only one element, the number 56, in it. Let's do the next one. So, negative 1 times 2 plus 4 times 8 So that will be negative 2 plus 32, which is 30. And now, if you look at this third example, this actually doesn't follow the rule that we just had, because this rule worked for only 2 elements. Technically, we'll get to the rule that covers this in a moment, but I want to point out how this pattern is going to work. We're going to do the same thing with this larger setup. Notice that I have 3 elements in my row and 3 elements in my column. And I'm going to do the same thing, except instead of just 2 things getting added together here, I'm going to have 3. So 2 times 10 plus 3 times 5 plus 4 times negative 1. All right, 2 times 10 is 20 plus 15, so that together will be 35, plus negative 4. Well, 35 plus negative 4 is 31. So now, let's have our rule that covers these bigger situations. So we've got a rule for multiplying a row matrix times a column matrix when they each have n elements. And here n can be any number. It is important that they have the same number. Notice that the pattern that we have been using relies on pairing them up, and that is going to continue to be the case. So notice that also this, I've got my row matrix has A sub 1, 1, A sub 1, 2, A sub 1, 3, dot, 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 A sub 1n. And the dot, dot, dot means the pattern continues up until whatever number n is. So if n is 15, you've got 15 elements in this matrix, all arranged in a single row. Likewise, with my column matrix, I've got B sub 1, 1, B sub 2, 1, B sub 3, 1, dot, dot, dot going down, B sub n, 1. So let's start multiplying these together. We're going to go in order pairing these up. So A 1, 1, B 1, 1, we pair the first 2 together, plus A sub 1, 2, B sub 2, 1. My second elements get paired together, plus A sub 1, 3, B sub 3, 1. So my third elements got paired together, plus dot, 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 A sub 1n, B sub n, 1. And I have just enough room on my paper to close off that matrix. Whoops. And so here is my rule for multiplying a row matrix times a column matrix for any number of elements. I'm still pairing up the first 2 and multiplying them together, adding that to the second 2 multiplied together, plus the third 2 multiplied together. All right, so let's have some more examples now. Move the rule out of the way. And here we go. One thing that we should note before we abandon this rule, all of these things got added together, and so this is a single number when you actually calculate it. So this product, the result of the multiplication, is a matrix with a single element. So that's a 1 by 1 matrix again. So now let's actually do these examples over here. All right. 2 times 5 plus -1 times -3 plus 4 times -1 plus 0 times 17. All right, so 2 times 5 is 10. -1 times -3 is +3. And maybe we'll show out all of this work. Plus 3. 4 times -1 is -4. And 0 times 17 is, of course, 0. So, 10 plus 3 is 13, minus 4 is 9, plus 0 is still 9. And so that matrix is the single element matrix containing the number 9. And next, so I have 1 times 12 plus 0 times 13 plus 5 times -2 plus 8 times 0 plus 2 times 7. And then we'll simplify this a bit. When you're doing these yourself, you can show as much or as little work as you're comfortable with. Different people have different comfort levels with arithmetic in their head. So I can ignore the zeros really, because I'm adding those. Adding 0 doesn't change anything. So 12 minus 10 is 2. Ignore the 0, plus 14 is going to be 16. So that is the 1 by 1 matrix with the number 16. And finally, one last row times a column. So I've got the matrix, the row matrix, 18, 4, 3, 7, 0, 9, and the column matrix, 4, 3, 2, 6. And we could dive in and start trying to match things up, but if we did that, we would notice before we got to the end that we ran out of things to match, because this row does not have the same number of elements as this column. So this product is not defined. And when I'm given a problem like that, that's all I have to say. They don't have the same number of elements, and so they are not defined. Now, it is only in the case where you have a row times a column where you're looking for the same number of elements. In our next video on matrix multiplication, we'll look at the general case. If it's not a row times a column, what do I have to look for in the sizes in order to be able to multiply?